A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good day. Thank you for watching this video. Today I'm going to talk about the acceleration and force measurement. From the title, it's about dynamic measurement. This is a very important topic under the subject sensors and also in the discussion of mechanical measurement and instrumentation. And then it's clearly about the vibration measurement. We will go on the introduction of vibration measurement before we can go further. After that, we'll go the subtopic under the vibration measurement, and also we're going to look at the related transducers about the vibration measurement. So as an introduction, so why we need to measure vibrations? There's a lot of reasons why we need to measure vibrations. First, if I can mention here, is actually the to detect the shift in the omega n or natural frequency of the system, which is the shifting of natural frequency will indicate possible failure to the system. And next, we also can select an operational speeds. Of course, to avoid resonance, appropriate a suitable speed can avoid the resonance, because we know resonance is if the speed of the source of vibrations close to the value of the natural frequency, it will move at the very huge amplitude, which is the resonance. And it will of course it will cause the damage to the whole structure lah. And also we can use the measurement of the vibrations, the result of the measurement, to validate or to verify the approximated model that we do. Basically in design stage, we do an approximation. We do calculation on the model. We model the whole structure before we can proceed with the fabrications. So to verify the model, we measure the vibrations. It's close with the theoretical value that we plan at the design stage. And also we also can identify mass, stiffness, and damping of the system of the structure during its operational stage. All right, and sometimes we measure vibrations in order for us to design appropriate or suitable isolations to the vibrations. Moving forward, the vibration or the vibration measurement. This is actually the block diagram for the vibration measurement. First, we have input, which is the vibrating machine or vibrating structure as the input. So we use the transducer, which is in this case vibration transducer or vibration pickup as the transducing element. And then after that, we of course we go to the next element, which is the data conditioning element. For this case, is signal conversion instrument with that we convert the signal from mechanical into an electrical signal. And then we have signal processing and display in the either in recorder unit or in the computer. And then after we have complete the acquisition, either we store or we display, and then after that we do data analysis. Basically, data analysis is basically for the vibration measurement. Usually we collect the data and then we will do post processing of the data, because we deal with the huge amount of data. So it's very important for us to do post processing. Sometimes we cannot display the data in real time, because of it have a problem in terms of um, memory of the data. Sometimes if we not properly select the system, it will have lagging in terms of showing the results of the measurement. That's why we have to optimize the, if you look at the theory for the instrumentation, for the vibration measurement, we need to find an appropriate sampling rate that's suitable for the measurement in order for us to acquire a real-time measurement. Otherwise, we just collect the data and store it, and then we will process later. We will view later as a post-process data. All right. So it's very important for us to look at the frequencies, the range of frequencies and amplitude for the measurement. Before we proceed with the measurement, we have to expect the frequencies and then the amplitude, the possible amplitude of the vibrations, and then we have to look at the size of the machine, of the structure, and then we have to look on the conditions of operation of the machine, either is harsh condition or either is actually a safe condition for us to measure. Because different condition, we need to use a different kind of sensors actually. Different type of sensors, different type of mounting sensors to the structure. There's a lot of consideration, so we have to look closely of the system before we can proceed with the selection, proper selection of the transducer. And also finally, the type of data processing that we want to use. As I mentioned earlier, this is actually a dynamic measurement, so we deal with a lot of sample data, so we have to carefully plan on the type of data processing that we want to use, because we don't want to sacrifice in terms of data, real-time measurement data. We don't want to have a lagging in terms of measurement. If we have lag in terms of showing the actual measurement, it will give a false representation of the data. So we have to be careful on the type of data that we want to process. All right, so we're gonna look on the a few type of transducers that will be used frequently for the vibration pickups or vibration transducer. First is we're gonna look on the variable resistance transducer. This kind of transducer is based on the strain gauge, basically strain gauge. The strain gauge will paste on the cantilever beam. We have cantilever beam here that connect with the mesh. The whole cantilever beam is fixed on the base structure. We see the base structure will move together with the vibrating body. Okay, it will put on the vibrating body. So the base will move together with the body. If you imagine that mesh try to remain at its position, imagine the base is moving up and down. So the mesh here will try to move, try to stay at this position, and this cantilever beam is functioned as this spring. It's functioned as a spring, and it has its own K, stiffness. Okay, but this K here is not a stiffness of the spring, but this K here is actually is the gauge factor of the strain gauge. If you refer back to the previous lecture, I usually put it as G, gauge factor. But for the sake of discussion in this topic, it use the K value. But do not confuse with the K of stiffness. This is different. So basically, the strain value is equal to, if you can recall back the theory about the strain gauge. So the strain is the change of L length over the original length, or if you can convert, the change of R resistance over the original value of resistance times K. K is the gauge factor. Okay. Okay. So the whole strain gauge will connect to the leads, and leads, these two leg here will connect to the sorry, we got it with the either voltage sensor or voltmeter or whatsoever lah, that we can use for to measure the voltage. Alright, so next is this K here that I mentioned earlier. This gauge factor is referring to the change of R, so the change of R over R divided by the change of L over L. It's actually come from this relation here. It's come from this relation here. So if you move K as the subject that we want to measure, so it turns to be like this, or it can be approximately equal to 1 plus 2V, which is V here is indicates the position ratio of the wire. Okay, but the thing is K is given if you purchase any strain gauge, it will give the K for the strain gauge. Alright, so move it towards. Now this is actually the structure of the strain gauge. If you want to use only one leg, we choose either R1 or R2 or R3 or R4 to be the leg, yeah, for the measurement of the strain on the cantilever beam. Okay. So we know if you look at the structure here, if the M here, I forgot to mention here, if the M is vibration, if it vibrates due to the motion of the base, so the strain here is related to the vibration of the M. The strain here is linearly related to the vibrations here. If this displacement of xt moving downwards or upwards, this strain here will indicate whether it's positive strain or negative strain. Okay, that's you have to put in mind the relation between the displacement of x with the strain value. So the R1 or R2 or R3, R4 can be the leg, yeah, to measure the strain. And then it's actually the general equations for the measurement. So E is the value here that we want to like I mentioned earlier. We have to measure the E, the voltage, in order for us to track the changes of the resistance due to the strain, of course, to the strain. So E is equal to this equation here times the V, which is indicate the voltage of input. This is actually a fixed voltage. It's actually it's always fixed. We give the value, but this is actually the one that we want to measure lah. So so this equation here, if you go further, the delta of E, the changes of E, is equal to, this is for the case of in the beginning of the measurement, the E is 0 because of E0. You know, E0 means that if you look at the whole structure here, is in balance mode. If you don't know what I'm talking about, please refer to the topic of strain gauge or temperature measurement, where I'm talking about the balance condition of the Wheatstone bridge. So for the balance condition of the Wheatstone bridge, the R1 and R3 is equal to R2 and R4 times R2 times R4 is equal to R1 times R3. Okay, so if we pick one leg and then use as this measurement, so let's say Ri, and it have changed by delta Ri, so it can be written down like something like this: V times R naught, Ro, or Ro is referred to this one, either this one or this one, either one, depend on which one we want to use. Okay, it's the same value, and times delta R1 for R1 minus delta R2 minus R2 plus RT. Why they mention we do this arrangement? Because we don't know, either we want to use R1 as the measurement leg, or R2 as measurement leg, R3 as measurement leg, or R4 as measurement leg. We don't know which one. But this is for the sake of generalization. We want to make it general. Okay, let's say we want to use the R1, okay, as the measurement. Uh, uh, if the leads are connected between points A and B, okay, if you look at the structure here, if leads A and B, which is we use R1 as the measurement. So let's say R1 is equal to Rg, meaning R gauge, and then delta R1 is delta Rg, R gauge. And if this condition, if this is happening, which is all the other delta is equal to 0, because we only use one delta. So all this it becomes 0 lah. So of course if this is 0, so this whole the whole term here is 0, and then this one is also 0, this one also 0. So remaining delta Rg over Rg, or delta R1 over R1 lah, because we know that Rg is equal to referred to R1. And then of course times by Ro, and V is equal to V fixed value, voltage value fixed. Then it's become something like this. So delta Rg, if we from this equation here we manipulate, then we can find, at the end delta E, okay, delta E is equal to K VR strain value, okay, because delta R over Rg is equal to K strain. Okay, if you not understand how is this derived, you can refer to the previous slide. It's mentioned the relation between delta Rg of Rg and delta E over V R naught. Okay, so the bottom line is actually we have the relation between delta E with K, the gauge factor, and V, the voltage, the fixed voltage, and the R naught is this one, either this one or this one, and then the strain value. So the strain value is the one that we want to measure. So we can find delta E, so that we can find strain value. All of these are fixed value. All of these are fixed value. Okay. All right. So now this one is a theory on if you use variable resistance for the measurement of the vibrations. With the same structure, we also can use piezoelectric transducers. The bottom line is actually the fundamental is we want to find the change of voltage due to the vibrations, because the change of voltage will indicate the strain value, the change of strain. So for this case, if you use piezoelectric transducer, the voltage that generated, the charge that generated from the motions of xt can be related with the equation here. So first, we know that for the piezoelectric piezoelectric materials, the charge, the Qx, is equal to Kf. K is the piezoelectric constant. If you have charge, if you have force acting on the piezoelectric materials, if you can go further, the F is equal to A at the area of the size of the piezoelectric structure, and the pressure that acts on the piezoelectric materials. So if you look at here, we have the same. If you can imagine the same concept, the difference is this one is a spring, the previous one is cantilever. Why they use cantilever? Because cantilever can be used to paste the strain gauge. But if we don't, if you're not required to have something to paste the strain gauge, we use spring. And then for this case, the spring just hold the mesh. The same concept, the base will move, and the mesh will stay at the position, and it will have the xt as the motion of the vibration, and then the x value, the motion, can be related directly with the piezoelectric. Of course, mesh will give the pressure to the piezoelectric so that it will create the charge through the leads here. So the changes of E. Now this one is quite easy compared to the strain gauge. Just a simple equation. E equal to V. V is the voltage sensitivity times T, the thickness of the crystal, and P is the PX, the pressure of the force. It's related to force, pressure from mass to the piezoelectric materials. So if you can look at this example, so we have a crystal that having thickness of 2.5 mm and subjected to a pressure of 50 psi. Okay, find the output voltage of the if the V, or voltage sensitivity, is 0.055 p V meter over N. So just plug in the value. First, we know that the voltage sensitivity is in unit of V, voltage, and meter and Newton. So that's mean 50 psi need to be converted into Newton meter first. Then that's the conversion factor here. Then just calculate straight away. We give the 47.4015 volt. So it's quite huge voltage. 45 volts is quite huge voltage, because I think 50 psi. We usually feel the pressure of our car have tire about 30 psi. So 50 psi is very huge amount. That's why it got about 47 volt of the electric charge from the piezoelectric. All right, so we look at the variable resistance. Now we looking at the electrodynamic transducer. Also related with the vibration, but now we're looking at the velocity. And in the previous one, we relate with the xt, the displacement of the M. It's relate with the strain and also the piezoelectric charge. Now for the electrodynamic transducers, it relate with the velocity of the movement, a moving body. So if you look at this structure here, is based on the coil and the magnet. So the coil move in the magnet. So we have a magnet here. The whole structure is a magnet. So this coil will move with certain velocity, and it will create the voltage. The voltage. So the voltage is equal to D LV. D is the magnetic flux density. L is the length of the conductor. The more the length, the more voltage can be created, and the V is the velocity conductor. So if you look at the equation, so dl is equal to E over V or F over I. Okay, I'm not sure what's F over I. Maybe in terms of current. I believe I equal to current. Okay, F maybe due to force, but never mind. The most important is the E, the voltage is equal to D. L is the length of the conductor, and V is the velocity. Velocity of the conductor that relative to the magnetic field. Okay, look at here. The velocity is moving upwards. It depends on the directions. It will create the E. The more the velocity, the faster we move the coil. The faster the coil move in between the magnet, so it will create more voltage. Okay, so it's the same with the fourth type of transducer. which is the based on linear variable differential transformer. In the electrodynamic transducer, it uses coil and magnet, and for this one, it have two coil, two magnet. It have one core, but have two coil here involved. The first coil is for the input, and the other coil is for the voltage generation generated voltage, as the output voltage. So this is actually the first coil. Okay, it move in the, you use the same magnet core, but this is the first circuit here. Okay, this circuit is for the generating the voltage, and then this actually the input. So this will continuously giving the voltage to the whole structure, and it will initiate the magnetism to the structure, and that magnets will cross with the coil here in the second coil. Then it will definitely creates the voltage output. Okay. So but this one is depend on the, we need to have input we need to have input for the this kind of sensor. Okay, it's fixed input, and then we have output. If we don't have we don't have EI or input voltage, this E output is of course becomes zero lah. No input, no output. So if you compare with the previous one, this one is only totally on generating the voltage due to the motion of the whole structure, the whole coil and the magnet. But for this one is for the LVDT or a linear variable to differential transformer, is depend on the input voltage, the primary coil that give the magnetism to the core, and then it will cross with the other coil and generate the output here. All right, but this one, of course, because of they have its own input, it can give a huge amount of voltage change. For a small displacement, we can give this big output voltage, which is, for this case, we can have a very sensitive measurement. Of course, a sensitive measurement will leads to the more accurate measurement compared to the just pure coil and magnet. Okay, so this is another view of the LVDT, linear variable differential transformer. All right. Then we go to the accelerometer. We look at the accelerometer. What is accelerometer? Accelerometer is a device that that measures acceleration, including static measurement as well as the dynamic for dynamic measurement. Most of the accelerometer in the market, they're using piezoelectric based accelerometer. We have after this we're gonna see the type of accelerometer. I mean the details of the accelerometer, what is inside it. But in the previous slide, I have already explained the fundamental of how the vibration pickups, the vibration pickups, including the accelerometer, as one of the instrument that can be used to pick up the vibrations. So basically, as mentioned earlier, this is actually a single degree of freedom mass spring system, and it's combined together in one package, and you can see that the example of the accelerometer is as in the slide. You can Google. There's a lot of example, and in our lab, in vibration lab, I have a lot of example of accelerometer. In fact, in the lab also we try to build our own accelerometer. So this accelerometer is the output of accelerometer is the as I mentioned earlier, is actually electrical electrical output, either from the strain gauge or from the piezoelectric or capacitor as the capacitor if you use a capacitor base. All right. So the output of the accelerometer is proportional. The electrical charge or electrical signal is proportional to the accelerations of the body that we are measuring using this instrument. So this is actually the internal construction of the accelerometer. If you can see to the left side, it is example of the accelerometer is a single axis accelerometer. You can see that if you can show here. This is actually a screw that hold everything inside in the accelerometer. We have a mass, seismic mass as an M. If you look at in the figure here, it's an M, and then we have the piezoelectric crystal component that absorb that mass and convert it into, give the output of electrical output, so that it can go to the display. Okay, so for this one, the piezoelectric crystal is function as the spring and also as the damper itself. Okay. So this I have a case and everything, and we have this one is has a mounting stud with screw-based mounting stud, and then we have a little bit integrated circuit to make sure that some of the accelerometer have a pre-amplifier before the signal goes straight to the cable. Sometimes it need to amplify the signal before it can go to the DAQ, data acquisition. Okay, so basically, if I can show this construction or real construction of the accelerometer into a circuit, sorry, not circuit, it's a mass, a spring mass relation, spring mass damper relation. This is something like this, So so it will in terms of the position of mass, you go up and down. It's go up and down. The mass of position is linear with the acceleration magnitude. So the more m moving, the more displacement of the m, the more acceleration of the body, the one that we want to measure, the object that we want to measure. All right. So if you look at here, we have 6 accelerometer with 6 type of mounting. So maybe we can discuss together what kind of based on this the results of the measurement. We can discuss which one is the best for the to be used as the mounting for the accelerometer, because for measurement of the acceleration, we have to put the accelerometer on the body, attached to the body, so that the vibration will transfer direct to the accelerometer. So this from the figure, we can see that we have a 6 type of mounting. We have a hand probe, which is connect the accelerometer with the probe. Okay, it's a very long probe here. It can be long up to the user. Up to the application that you want to use. Sometimes can go up to 30 centimeter. Okay, and then we have magnet. We have type of magnet. We have 2 type of magnet, either dual rail magnet. We have a flat magnet. This is the one that we have in the lab. A flat magnet. It's quite good. We have a very strong magnet that we screw on this accelerometer, and then if we have a metal surface, we can just put a magnet so that it can transfer the vibration direct to the accelerometer. The thing is, we need to choose a very strong magnet. If we wrongly choose a magnet, they have a very low magnetic. So that means that will result on the transmissibility problem, and also it may jump due to the huge vibration. We also have a mounting pad, like a surface of mounting pad here. The pad I think it's some sort of adhesive. Okay. So we have also adhesive mounting. For example, beeswax. Sorry, not we, beeswax. And then the best one is this one. It's stud. You just screw straight away the accelerometer to the body. Okay. But this one, this kind of sensor, it non-detachable. And then basically this one we do for continuous monitoring lah. But some of the body they don't want to have any objects attached to the body during its operation. For example, motor or pump. So basically we don't put the accelerometer all the time at the pump. We only measure the vibrations at a certain period, a certain schedule to check whether the pump or motor have a huge vibration above outside the range for the acceptable vibrations. So that meaning that the pump or motor have some sort of failure or damage, or they need to be replaced with a new one. All right. So looking at this 6 type of mounting, so we can see that the number 6 have very low sensitivity, but we have a broader range of it's not broader range of frequency, but it have uncertainty in terms of frequency. The frequency is uncertain, so basically the accuracy may be questionable, but it did a job to measure the vibration, but maybe the accuracy of the frequency maybe is can be questioned because it give a very broad frequency measurement. Okay, and also the sensitivity is quite low. The same if you go to the number 5 and number 4, and then you can see the best one is number 1. Like I said, stud mounting is the best one because it's attached to the body. The problem is some of the body structure cannot be permanently we put the accelerometer on the body or on the structure. All right, so then we look at the next class activity that maybe we can discuss together. We put a brain to think about it. So we have this one, one of the piezoelectric sensor. So looking at the figure, we can see that the sensor have, if we look at the Y, it's a dB, the decibel, the amplitude of the vibrations that it can be acquired. And then look at the x-axis is the range of frequency. So looking with this one, is it considered as a narrow band sensor or wide band sensor? So the spectrum frequency is, we call it band. So if I'm looking at this one, my opinion is this one is actually a wide band sensor, but if you look at this 500 hertz, it dropped a bit. So that's mean that we have low accuracy in terms of amplitude at this level, 500. So above that is okay. So we can say that this kind of sensor can work properly, or can give a very accurate amplitude at 600 and above, up to 2000. But for the range of let's say 480 to 520 hertz, kilohertz, it may have a problem in terms of sensitivity, low sensitivity. Same as if you look at the earlier frequency, the lower frequency, for example 200 and kilohertz and below, we also have problem with the accuracy. But below than that, I mean, for example here, this one, I believe 50 and below, 50 kilohertz and below, of course it's not really good at all. So I can say this is the wideband sensor, but you have to be careful on which area, which range to be used to use this accelerometer. Okay, if you look at this one, okay, this is actually a frequency response curve, the same as this curve actually. but this is actually theoretical. So if you looking at this one, so at the certain range is flat, which is flat, but at some range is have a very huge resonant frequency, which is this is actually the one that we have high sensitivity, high sensitivity to the sensor. If you choose a 3 dB response range, that means from the flat area, if the value reduce about 3 dB, still you can consider as in the range as well. Below than that, for example, this one is 0. So if 3 dB is negative dB, so we can still consider as a flat range. Flat range. So over than that, consider as uncertain, because it fluctuates. It go down and up. So we say the value of response is uncertain. So if you look at here, this is one of the spec. So if you look at the specification of the accelerometer, frequently they use a frequency response in 3 dB. So that means that we have a flat response, and then it dropped a bit. 3 dB still considered as the a flat response. So that means it's still in the range. So that means that's why it's meant by the nominal 3 dB frequency. Some of the measurement they use a plus minus 5% response range or 10%. So it's up to the measure. So when we look at the specification, we know what's it mean by the specification. So for example, not related with the graph to the left. It's actually the table here is different, the different explanation. So if you look at the model here, you have let's say for example units 2210 002 here. So the input range can be about plus minus 2G. So which is a quite low G. G means 9.81 meter over second square. So quite low range in terms of amplitude, but in terms of frequency also quite low. So this is actually nominal frequency, which means that it can works up to 0 to 300 with a flat surface, with a flat frequency. So that's mean by maybe after 300, it still get the frequency, but it's not flat. It's fluctuate or it go down, or it might have a peak as a resonant frequency. But that one can be considered as uncertainty because it's far from the flat frequency. And then, but for this one, for this range, it have 2000 millivolt over G. So every G it will give like 2000 millivolt. So quite huge sensitivity. So quite sensitive. But in this range only. Okay, in this range only. Otherwise, it maybe have uncertain and not accurate in terms of readings. For if you get the second one, for this one, the plus minus 5G, quite big range. Okay, but a response in terms of 0 to 400, but sensitivity is 800. So and then same goes to the further model. It have like for example this range is increased. The nominal frequency response also increase up to 10,000, but sensitivity usually if you have a broader range of sensor, the sensitivity become low. If it's related to this graph here, if you have broader range here, usually it's in a very low sensitivity, but this one area here have very huge sensitivity, but in terms of range, it's very small range only for this kind of measurement. Okay, that's how you read the specification of any accelerometer, and then when you want to choose for the correct accelerometer for your application. All right, so finish with the accelerometer, the specification. Hopefully that after this you can choose the best accelerometer for your application. And then if you look at this one, we also have a force transducer. So of course we have F equal to MA. When we discuss about the vibrations, it's actually related to the force as well, because any acceleration is because of the existence of force. Okay, so force can be measured by many method. So one of the method is by measuring, of course, A, acceleration. Okay, so that we measure the A and then we can find the F lah. Okay, so we have A as a acceleration to calculate A. Then how can we measure M? Okay, mass is, we have a lot of experience measuring the M as the weight measurement. We have all, everyone, I believe everyone of us already know how to measure, have their own instrument in their house to measure their own weight. Okay, but the fundamental of the weight measurement is they use either the load cell or the pneumatic load cells or the electronic load cells, or most fundamental of measuring mass measurement is the using mass balance instrument. So we go have a look on this one. So for example, if you use a load cell is actually a design of better I just show you the shape. So this is the shape of the load cell. You have a lot of design. You have cylindrical block or rectangular block, proving frame. This is actually one of the complex shape, this one. But all of this shape actually, when we have force or yes, I believe force or weight that act on the top of the shape here, it will deform anywhere. For example, for this cylindrical block, it will have some kind of compressive strain at this middle here. So we just measure this strain, and then we can relate to the mass that acts on here, the force due to the mass that acts at this area. Ring, if we put mass, it will give force, the weight to the whole ring, and it will deform the ring. And then we put any strain gauge or whatever to measure the strain. The same with the rectangular block, and also all this shape, they are actually deformed due to the existence of the weight because of the mass. Then we just put the strain gauge, and then you can measure the we have the relation between the mass and the electrical signal produced by the strain gauge or piezoelectric strain gauge or optical strain gauge. It depends on how we want to capture that strain. Okay, so that's actually the basic of the electrical based load cell. I have a lot of you can find this one in the Lazada or Shopee or Amazon or eBay. You can find the load cells. So first, if you purchase this kind of load cell, you have to calibrate because it produces the electrical signal. How can you calibrate the electrical signal with the correct mass? I have purchased one in the lab. So what I do is I need to have a standard mass like 1 kilogram, 2 kilogram, 5 kilogram, and I need to plot a linear graph to that so that I can find the relation between the mass and the electrical voltage or ampere that produced by this basically voltage because we use strain gauge. It varies the voltage, so we relate the voltage with the mass so that we can find the sensitivity of the load cell. You can do it by yourself. You just purchase this one. I think it's not really expensive. Some of it can be like 50 ringgit. Some of it 100 ringgit. It depends on the size and the sensitivity of the load cell. All right. So then we move to the another type of mass measuring device, which is the pneumatic or hydraulic load cell. The same as the same concept as the electrical base. It must induce some sort of movement. If we look at the previous load cell, it deform. The deformation can be sensed, detected by strain gauge, sorry, strain gauge also, and also the piezoelectric gauge. For this one, it produce some sort of deformation in the air gap, because if you put not the air gap, it's actually the air pressure. The air pressure. If you put a mass, very huge mass, the pressure inside the air will be uniform, and it will transfer along the line that have the same air. For example, we have this one. Okay, if we have air along this tube, the pressure is uniform. Either we put a pressure here, the pressure starts here, but along the way in the pipe, the pressure will still remain the same. So if you can relate that air pressure with the mass, then we can find the mass. We put if for the electrical base load cell, we relate between mass and the electrical signal, the voltage. But for this one, we relate with the mass and the pressure of the air. Not on the air, we can use the fluid as well. So if you use air, it can be a pneumatic. If you use fluid, for example, oil, it be the hydraulic type of load cell. Either pneumatic or hydraulic, both of this load cell, usually we have a big range of measurement, a lot of huge mass, big mass. For load cell with electrical signal, basically we use for the small scale of mass, small mass. All right, so sorry. So that the last one is actually the mass balance instrument. This one actually, if you look at the picture here, is actually common one. You can see this one is we have in the lab. So you have this actually unknown mass that we want to measure, and then you put you just move the mass here, and then when it's balanced, so you put the null marker here. If this achieve the sign here, that means it's actually in the balance mode. Then we can find the accurate mass for that actually balance same with the mass here. Okay. All right. So and also you can use the old one, the simple one. You put the unknown mass here, and you just put a number of mass, standard mass, to make it balance here. This is a very old method. Okay. There's a lot of mass balance. Out of all this method, load cell, electrical based load cell, pneumatic load cell, I think the most accurate is this one. The most accurate is one, because it's actually put comparing with the real mass, Okay, but pneumatic load cell or electronic load cell, they can give a consistent measurement. In terms of consistency, fast measurement, you can use load cell, electronic, pneumatic or hydraulic. But with this one, it gives the most accurate. But this is a manual method, so it takes time to get the accurate measurement. All right, so now we move to the we look at the accelerometer, and then we look at the how to get force, which is basically using accelerometer and calculating the mass. And then this one is torque transducer. So for torque transducer, we have three methods, three common methods. The first is by using the measuring the reaction force of the shaft. And then you have second one is pony brake, and the third one is measuring the strain produced by the rotating body. Of course, when the body rotates, it will have some sort of twisting effect, and that twist actually produced by the torque. And then we can measure the twisting using strain gauge or any gauge that can measure the strain. So we look at this transducer one by one. So this is actually the torque sensor. You can Google. There's a lot of example of torque sensor available. Basically, this one, yeah, this one is dynamometer. So we have a motor that work in this area here. Okay, so it coupled with the dynamometer. Inside the dynamometer, it have like some sort of a power absorber. It tried to hold the movement of the motor. The more power the motor, the more power absorbed by the dynamometer. The power that absorbed by the dynamometer, it translates into the force. Force. So, for example, here force here. So, how much force detected in this area? We times by the L, the length here. Then we can find the torque. So basically, if we couple the motor with the dynamometer, it always move. When the motion produce the force, it will have force always pushing the arm here. Okay, the cradle and the arm. And then with the certain with a fixed amount of force, we measure the force, and then we times by the L, and we can find the torque. All right. So the pony brake, okay, is a simple, is a mechanical system. If we have we put the pony brake around the sorry, it's actually a brake, it's some sort of brake put together with the couple with the moving shaft or whatever. It will try to rotate the drum, and that rotation will pull the spring. This rotation here, we pull the spring, and then we can measure the force in here in the spring. Yeah? We measure the force of the spring, and then we can relate to the torque that actually as a source of the movement here in the shaft here. Okay. So the equation is something like this now. So the Fe is the force exerted by the rope. Okay, the mg is the mass, the dead load here. Fs is force of the spring. So the Fe, the force, okay, is equal to the mg minus the Fs, force that measured at the spring. Okay, then we can find the Fe. That's how the pony brake works. Okay, and then from that Fe, you times by Re. Re is the rope radius. Okay, and you can F force times with the R, the radius, you can find the T, torque. It's actually that's the concept of how the torque was measured by pony brake. And then the last one is the strain by the sorry, if I can put the figure here. So this one's actually, if we have strain, okay, it will deform or twist the shaft a little bit. That the twisting is linear related with the strain. Sorry, the torque. The more torque, the more twisting phenomena that happen to the shaft, but you will not see that on naked eye lah. Just put the strain gauge on any location there. You can measure the strain. Okay, you can put a lot of places. For example, you can put 4 places. For example, like this one, and then you can have more accurate measurement. So you know how strain gauge is working. We have in the previous slide. So just measure the strain, relate with the you have a linear relation with the torque measurement. Okay. All right. So this torque also sorry, the power. If you look at here, the power is equal to torque times RPM. Or if you can find the power value here, okay, and then we measure torque, we also can measure the RPM as well. Okay. Okay. All right. So so I will skip this one because we know how the strain gauge works. All right. So this is actually, like I said, we have a power equal to torque times the RPM. So this is actually how to measure the power. Okay, so I will not go detail on this one. So I just skip this one, and then all right. So that's how the torque measurement. So we have three type of torque measurement. We have first one is the um, dynamometer, and then we have a second one is the pony brake, and the third one is a strain induced measurement. We measure the strain due to the twisting because of the torque, the existence of torque. And then last one I want to show this tachometer. So I think this, you can see this one in the lab. I will show in the lab later on. This is actually digital tachometer. We have a lot of tachometer. You can say the concept is like a stroboscope. Tachometer is want to measure the RPM. If you have a power meter, you have a torque meter, you can calculate for RPM. But if you measure RPM directly, and then you know the torque from the motor, you also can reverse to find the power that need, or power that produced by the motor. All right. So tachometer or stroboscope also can be used. Tachometer is based on laser. Stroboscope based on light. I think you have learned a stroboscope in the physics class at school. All right. So I think this is actually the end of our class for the for the whole subject. So hopefully that you have looked into the four important sensors, which is the strain gauge, pressure measurement, temperature measurement, and accelerometer. All this is integrated. So hopefully that you can utilize this one in the real applications in engineering. So thank you very much. I leave you with this one. I'm sorry for any lacking of information. So I will improve these videos in the future with your comments. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh.